Alright, so next we are supposed to start with the 13th exercise, but that is just, it asks us to prove theorem 9124. It is that theorem which gives us a necessary and sufficient condition for a subset of the real numbers to be closed and bounded in terms of sequences. So we already have proved this, so that means it's done for us. So let's see the next one. In this next one, we have to show that any finite subset of R is closed and bounded. And in this proof, we are going to use this theorem. So let's see the solution. Let A be a subset of R, and let this be finite. Okay, now let us handle the case where A is the empty set separately. If A is the empty set, then we know that A is closed. Why? Because we have already seen that the closure of the empty set is the empty set itself in a previous result. So by definition, the empty set is closed, that means A is closed. Also, A is contained in the closed interval -1, 1 say. In fact, A being the empty set would be contained in any such closed interval whose middle point is the origin. Origin means the real number 0. And so, by definition, A is bounded as well. So we can now assume that A is non-empty. Now A is a non-empty finite set, since A is finite. Any sequence xn where m is some integer of elements in A, or in short, any sequence in A has a constant subsequence xn I say, where I, well, there is actually no need to start the index from m, we can just simply start it from 0. There is no need to be needlessly general. So here also we can make I vary from 0 to infinity, i.e. xni is equal to C for all natural numbers I, where C is some fixed element in A. But why is it like this? That is because, you see, any such sequence has by definition infinitely many terms. Now those terms are supposed to all come from A, but A is finite, so repetitions are, you will have repetitions. There is no getting around that, okay. and that too because there are only finitely many terms in A. Some term will have to be repeated infinitely many times in this sequence. Let C be one such term or one such element. Now if you consider those terms only from the sequence, you then get a subsequence all of whose terms are the same, that is C, and that C is some element in A. But then Xni becomes a convergent subsequence of that sequence which converges to a point in A, and that point or that element is C. And that's why by that theorem A will be closed and bounded. Because what does that theorem say? It says one half of the theorem says that if in a set you choose any sequence, in other words, if you choose any sequence whose elements are coming from a set and you find a convergent subsequence of that sequence whose limit also belongs to that set, then by that theorem that set must be closed and bounded, and this is the case here. But then this is a convergent subsequence of Xn such that its limit C is in A. So by theorem 9.1.24, A is closed and bounded. So when A is non-empty as well, it is closed and bounded, just like the empty set. So that completes the solution. And then there is one more. Let E be a bounded subset of R. E be a bounded subset of R, and let S be the supremum of E. Be the least upper bound of it. There is no need to write more, we know what it means. And also the author says this however I want to write, and then I will show that there is a slight mistake in this. Note from the least upper bound principle, that is theorem 559, that S is a real number. That's what the author says. However, that is not always true. We need an extra assumption for that to happen. It's a small mistake, but nevertheless it's a mistake. By theorem 559, that S is a real number. But what do we have to do? We have to show that S is an adherent point of E. Show that S is an adherent point of E, and also we have to show that S is an adherent point of the complement of E in R. Okay, so let us first address this issue, this remark. Note carefully that we are just given that E is a bounded subset of R. Fine, E is bounded. So by definition, this is also possible. E can be the empty set because the empty set is bounded by definition. However, then in that case, the supremum of E is by definition minus infinity. It's not a real number. So we have to additionally assume that E is non-empty as well. Once we make that assumption, then it's okay. So let's mention that. We need the additional assumption that E is non-empty, and we assume that. Okay. Now let epsilon be any positive real number. This is our short way of writing that fact. Okay, that thing, that epsilon is any positive real number. We do not explicitly write that entire sentence. When we see this, we understand that epsilon is arbitrary and positive. Since S is the least upper bound of E. It is an upper bound, but it's the least upper bound. It's the smallest among all upper bounds. So if from epsilon, from S, we subtract epsilon, then this becomes a smaller number than S. Since S is the least upper bound, this even smaller than that number cannot be an upper bound. So because of this, this is not an upper bound of E, and that has its consequence. Is not an upper bound of E. So there exists some element Y in E such that S minus epsilon will be strictly less than y. This inequality tells us that S minus epsilon fails to be an upper bound of E, because at least one element of E exceeds this. There may be more such elements, but we need only one. We thus have this. However, S itself is an upper bound and Y is an element of E. So Y will nevertheless be less than or equal to S, which however itself is less than S plus epsilon. In other words, we now have this, or the absolute value of y minus s is less than epsilon. Now see what we have done here. We have assumed epsilon to be any positive real number, and we have been able to find an element y in E which is epsilon close to s, in the sense that its distance from S does not exceed epsilon. But then by definition S is an adherent point of E. Hence S belongs to the closure of E. Instead of writing S is an adherent point of E, we can just write S belongs to the closure of E by definition. So this is one half of the claim, but we have also been asked to show that S is also an adherent point of the rest of the real line, that is the complement of E. And for that we note this. Next, note that since S is an upper bound of E, S is the least upper bound, but let's concentrate on the upper bound aspect only for now. Since S is an upper bound of E, so this intersection needs to be empty. Why though? That's because in this interval all the elements or all the numbers are greater than S, strictly greater than S. However, in E, all the numbers are less than or equal to S. So there can be no intersection. So that's why this intersection is empty. These two sets are disjoint. But then this interval is contained in the complement of E in R. You understand that this interval is after all a subset of R, so it's inside R, but it does not intersect the set E. So you can think of the situation like this. This is say your E, this is R. Of course, this is not how we draw a line, but just want to show the Venn diagram. Okay. So this is R, this is E, and this interval, whatever set it is, it does not intersect E. So that means it's lying like this somewhere. this thing. So then automatically it is a subset of the complement of E in R. You can see that clearly, and you can prove that also if you want. So for some element Z in this interval, this Z must belong to the complement of E due to this containment. And also, what is the distance between Z and S? Let's look at this also. Because Z is coming from this interval, Z is greater than S. Okay, that is one thing. And as a result, Z minus S is a positive real number. So you can lift the modulus, I mean the absolute value. And the other thing is that Z is also at the same time less than S plus epsilon. So Z minus S will be less than epsilon. So we have shown that this number Z is epsilon close to S, but this Z is some element in R minus E, R difference E. So again, by the definition of adherent points, Z is an adherent point of R minus, sorry, what the hell am I saying? S is an adherent point of R minus E, because we have found, regardless of what epsilon is, we have found an element in R difference E which is epsilon close to S. Thus, S is an adherent point of R minus E as well. And that fact we can just write this to express that. Okay, so that completes the solution, and it completes this section also. We will start the next section, whatever it is, this coming Sunday. And our next upload is this Tuesday, next Tuesday. And on Tuesday, let's go back to number theory. So that's just it for tonight. Signing off. So see you on Tuesday. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.